Good afternoon. Welcome back to the PENC Virtual Raleigh Seminar. Again, I'm Katie Cox, PENC Membership Director. Thank you all for joining us. As a reminder, if you have any technical difficulties, please send me a chat in the chat box and I will try to assist you. We will take questions throughout the presentation today, so type those into the questions box and I will ask those out loud to our speaker. Today's presenter is Ken Delaney. Ken is Director of Industry and Innovation at the Freedom Systems Center, a smart grid research center headquartered at NC State. In this role, he manages industry relationships for the center, promotes the commercialization of center-developed technologies, and helps students make connections for internships or full-time employment. He also manages center marketing activities, including website, newsletter, and conference trade show booths. Prior to this role, Ken worked in air quality and industrial energy efficiency. He holds a BS in physics from Furman University, a bachelor's in mechanical engineering from Georgia Tech, and a master's in ME from the University of Texas at Austin. Ken, thanks so much for your time today.
All right, you're welcome. Great. Well, thank you for the introduction, and thank you again to PENC for giving me this opportunity. The goals today are just to give a brief overview of microgrids, and then also to talk about an open source platform that has the potential to really accelerate the deployment of microgrids. So quickly, introduction to Freedom. It's not that we don't know how to spell, it's an acronym, right? So it's the Future Renewable Electric Energy Delivery and Management System Center. We are headquartered at NC State University. We were started 2008 with a large grant from the National Science Foundation with a goal to take a systems approach to modernize the electric distribution grid on how to accept more distributed energy resources. That was a 10-year funding cycle. We achieved about 95% of our initial research plan with a few detours along the way. But currently we receive funding from the Department of Energy, the National Science Foundation, Department of Defense. Corporations come to us to fund research in these areas, and we're also sponsored by memberships from companies. So the research pillars where we do work can kind of be divided now into these four areas. Wide bandgap power electronics, and just to clarify, wide bandgap devices are different from your typical silicon based power electronics. Wide bandgap refers to, there's some physics part to it, right? It's the amount of electric potential required in the semiconductor for the electron to jump the gap. A wider bandgap means that your power electronics can operate at higher voltages and higher switching frequencies. That allows you to put more power into a smaller package. The primary materials for this right now are silicon carbide and gallium nitride. That's really the basis for a lot of the other work that we do. The capabilities of these wide bandgap semiconductors have opened up entirely new ways to design power electronics. So that's one area of our research. We also do work still within what we call modern power systems, and this is the traditional grid, but also all of the additional issues and features that come along with the incorporation of additional distributed energy resources. We also do work in electric vehicles. Like I said, we don't build the electric cars, we build the chargers to charge the cars, we build the inverters that control power flow from the battery to the motor, and we build even the high power density electric machines that will help drive whether it's electric aircraft or future electric vehicles. And then of course we also do work in renewable energy. Again, we don't build the solar panels, we make it much easier to incorporate solar panels into the grid. We do analyses for the utility companies on how they can integrate more distributed energy resources onto their system. And all of these images are from our lab. We have the PV array on our roof. We have a high bay lab space. This is the controller that we built. That's our research center Nissan Leaf that we're charging there. This is actually a commercial product available from a startup company that came out of Freedom, and that's a solid state transformer. And then this is an example of some of the things that are inside boxes like those. So that's very briefly about Freedom. But And you can learn a lot more at our website, which is freedom.ncsu.edu. But today, we're going to talk a lot about microgrids, which again is just one small piece of the research that we do at Freedom. We're going to step through examples, talk about the features, why are people so excited about microgrids, we'll talk a little bit about operations design, of course, control, and then get to the specific technology that's been developed at Freedom. So let me start with some microgrid examples. And you always kind of got to start with, what is a microgrid? Well, various organizations have definitions for this. The DOE has one. Standards organizations have their own takes on how to define it. But the one that I like is it's the section of the grid that can electrically isolate when necessary, but yet stay connected and provide grid services while it's connected. All of this happens through a single connection point, which is called the point of common coupling. Remember that for later. When we get to talking about other things. But it also helps to define what is not a microgrid. So just a backup generator, not a microgrid, because you're not providing services back to the grid. An uninterruptible power supply, again, not a microgrid. That's something that kicks on and helps to give you power certain devices, but usually not an entire facility or something the size of a microgrid. And it's more than just having solar panels. All of these examples of equipment can be included in a microgrid, but you have to have additional features to truly make it a microgrid. So this is the DOE, I don't know, it's the blob diagram of what a microgrid could be. You could have a microgrid that essentially, if you look at this, consider this as bulk transmission, you could have one that encompasses everything that's connected to the substation, again, through that single point of common coupling. But if you went further down, each of the section of the grid branches off into feeders. So you could have a full feeder microgrid, which is this darker area. And so this would be the point of common coupling. You could have partial feeder. So maybe this is a cluster of commercial buildings that may have some generation capacity and a single point of connection back to the macrogrid. It could even be as small as a single building, a single house. But again, with that single point of coupling back to the grid. So other examples, these are gonna, that's kind of the generic cartoonish version. Let's talk about some specific examples. This is an aerial shot of Butler Farms. If you've been in North Carolina for a while, you've probably heard of this microgrid or potentially the one at Ocracoke Island. This was partially funded by the State Association of Co-ops in coordination with the local cooperative that serves the Butler farm. And you notice this is a pig farm, hog farm, and Mr. Butler covered his wastewater lagoons, uses anaerobic digestion to generate biogas, and then burns that biogas in a generator, an internal combustion engine generator. But then the electric utility that partnered with him on this project added a little bit of solar and added some battery storage. So if the grid goes down, Mr. Butler powers his farm, but then also provides power to several of his neighbors in the area. A true cooperative microgrid. There are also remote microgrids. And when you think remote, you can think villages in Africa that have not yet been electrified, villages in India that have not yet been electrified, places that are way far away from a centralized grid, like Buckland, Alaska, but have the potential to generate their own electricity locally. In this case, they balance wind with a battery system to help power their village in Alaska. But they used to use diesel, which could be hauled in only certain parts of the year due to ice flows on the water. So that's an example of just, a place that's had electricity, was already electrified, but it was fairly expensive, very expensive actually, to get the fuel and the energy needed to where they could run their system. And then of course there are islands, right? Islanded microgrids is the classic example, is literally an island. And again, thousands of examples around the world where island, either countries or just island inhabitants, have to rely on importing fuel to be able to power their grid. In this case, this is on American Samoa, which is one of the examples where Tesla deployed a very large solar PV array and added battery storage to help back that up. So Other examples of microgrids, think military bases, right? That would want to have, and actually are mandated to have, a certain amount of backup generation, a certain amount of capability to operate independently from the grid for security reasons. Think town centers, maybe. If there's something like, I don't know, a hurricane, right? But they still need to provide emergency services even when the electricity goes down. And as opposed to having multiple disconnected buildings, they could have all of those connected as a town center and be able to provide perhaps longer services or longer duration services for their constituents until the main grid was able to return. Colleges, college campuses are another opportunity for microgrids. So there are lots of examples out there. But each of those examples have a few features in common, right? They've all got generation, whether it's through, for example, an internal combustion engine. This is an example of something that PowerSecure builds. This is actually, they use Volvo engines, but PowerSecure is a local company headquartered in Wake Forest, but then have their manufacturing assembly operations in Durham. They build very large microgrids and have deployed thousands of them across the US and around the world. And actually, PowerSecure was involved in the Butler Farms microgrid, and I know the Ocracoke microgrid, as well as others across North Carolina. But you've got generation, you've got loads, right? So obviously you're consuming that electricity somewhere, but you also have to have the ability to store that electricity. Tesla batteries, one example. Thermal energy is another way to store some of that energy. It doesn't allow you to convert back usually to electricity, but it is a way that you can store energy for later. And then you have to have control. All of these pieces have to work together. This is an example of an ABB controller that's integrated with a battery storage bank as part of some of their microgrid features. So those are some of the common features, but in addition, you have to have communications. So your generation has to talk to your storage, which needs to know what the loads are going to do. Because if you have multiple sources of generation, the ideal situation is that your microgrid is able to optimize which generation it uses when. Is it better to store some of the excess electricity from the PV array? Should I save my diesel for later? What's going to be the impact of cycling my battery on battery life? And you can optimize all of those things for cost, or carbon reduction, or other features. But in addition, you also need protection. So what happens if there is a fault? You know, how is your microgrid going to react? What are some of the backup cases? So you have to think through all of these things as part of the microgrid. But these are all common features of microgrids. So I got into this a little bit about why companies or individuals may install microgrids. And the number one reason usually that people give is for resiliency. And resiliency is defined as the ability to operate in abnormal conditions. Reliability is the ability to operate in normal conditions, but then when things are abnormal, that's when you want to be resilient. And it's the ability to recover from that abnormal condition. That's also kind of a piece of resiliency. But on the image here, I also show the cover of the North Carolina Climate Risk Assessment and Resilience Plan. And in this plan, the word microgrids is mentioned, you know, over 80 times because it's a potential solution to some of the energy disruptions that occur through, I don't know, again, hurricanes, right? And if we were in California, it would be wildfires. If we were in the Northeast, it might be snowstorms. And, you know, it's just the ability to, like I said, operate when things go wrong, basically. But then other reasons for microgrids. I mentioned, you know, the ability to integrate wind and other types of renewable energy resources. Customers often look to microgrids to integrate those renewable resources because the fuel value, the fuel cost is zero. You have capital cost to install the equipment, and you can average that out over life. But in essence, once you buy it, the electricity is essentially free. There are operations and maintenance costs, but in reality, you know, the energy that you're receiving is essentially free. And in the case of many of these renewable energy options, emissions free as well. So there are environmental reasons that, you know, some people, some organizations will use that as a reason to justify why they are putting in a microgrid. In the long run, though, it all comes down to cost, right? So if you're going to build a microgrid, somehow you have to justify the cost of putting that in. Is it because the electricity is going out too often? Is it because you do have these, your company has a carbon footprint reduction goal or a carbon reduction goal, and that this is one way for you to achieve that goal. But for a microgrid, you cannot forget some of the opportunities to generate revenue by providing these grid services back to the utility. And this is not true in all parts of the country, but in many parts of the country, you can participate in capacity markets, you can participate in frequency regulations. So there are various services that you can provide back to the main grid utility operator. You also have to calculate this value of resilience. And for food production facilities, for example, when they lose electricity, when they lose power and they have to go down, they can tell you basically the dollars per minute that that facility is losing, because anything that's in process, it may no longer meet safety requirements, and so it has to be tossed. So that's lost product, it's lost productivity, it's lost time. Any manufacturing operation should be able to tell you those kinds of things. It's harder to define resilience for an individual residence, right? I know I have friends in California that complained about losing an entire year's worth of their homemade pasta sauce. They grow the tomatoes, turn it into pasta sauce, and then PG&E shut off the power, and so they lost a year's worth of stuff because their refrigerator was without power for 5 days. I don't know that that's something that they will include in their value of resilience, but it's certainly annoying. The other opportunity for the value of microgrids is the ability to defer a capital expense. Typically, that's why a utility might install a microgrid, and utilities have done so. Their Southern California, Edison, I think, is the one that basically converted an entire town to a microgrid because the long distribution line that they had going out there was having all kinds of issues going across the mountains and through the desert. Duke Energy, here much more closely in our territory, has received permission from the Utility Commission to install a couple of microgrids as well. Again, mostly for remote locations. One was for a small town where it was going to be more expensive for them to add either an extra distribution line or increase the power capacity of that line. And so they installed a battery system that enabled them to help manage the power loads, the power needs for that remote town. So those are some of the values that you include. Of course, a microgrid is going to cost you money to install. So you have to balance those. What's the benefits? What's the cost? And for most people, these things of resiliency, environmental considerations, and cost are all intertwined. But that all goes into the decision about why you would install a microgrid. Okay, so back to the outline, just briefly. Talked about examples. Hopefully everybody understands what a microgrid is. And now I'm going to get into a little bit more of the technical pieces on operations and design of microgrids. All right, here's why microgrids can be complex. Because you're basically building a mini utility, right? You've got the same goals. You have to balance generation and load. You have to maintain power quality, both frequency, waveform. You've got to regulate voltage on your system. You still have to provide the safety that's required from electrical codes, but it's, you have to design your protection scheme for the microgrid. Where do you put your breakers? Do you need relays for the switches? Do you need all these other pieces? Which is where power systems engineers obviously get involved in helping to design these. And those are the kinds of things that they consider, but it's just another point as to how complicated it is. But wait, we're not done. You've also got to figure out, how do we operate our little section of the grid when we isolate from the microgrid, when we island, and then even when we transition back connected to the grid. And there are several ways you can do that. Some microgrids, again, when they detect a loss of power in the main grid, their microgrid will actually, it's designed this way, mainly for safety reasons, to go dark, and then they will bring things back up after a momentary outage, enough for them to disconnect a transfer switch between the main grid and the microgrid. NC State actually can operate several of the campuses of NC State can actually operate as a microgrid, but not with that seamless transition. They wait a period of time and then are able to power some of the loads on campus. But while you're in operating mode, you're either grid connected or you're islanded. And so again, we're adding additional complexity. While you're grid connected, your microgrid can participate in demand response programs where you would receive a signal from the utility that says, hey, loads are increasing. We'd like for you to decrease your load. Or, in that demand response program, participants are usually compensated for being able to reduce their power demand during that time. Or if you do have excess power, there is the potential that you could sell that back to the utility. Again, there are only certain utilities that can handle that or that have regulations that allow them to do that. But there is the potential for you to provide energy back to the microgrid. Like I mentioned earlier, you can participate in frequency response programs, provide voltage support, again, receiving signals from the grid. And the list goes on. There are, substantial pieces of operational requirements for microgrids that if you're going to derive that value, which is going to provide you to make that benefit cost analysis favorable, that you may need to be able to provide these services from an operations standpoint. And I haven't even talked about when you're not connected to the grid. So in islanded mode, you need to be able to form your own grid. Well, that requires some special programming on some of the inverters, which the inverter is the box of power electronics that can help control power flow. Typically, it's used for DC to AC conversion. So things like solar panels, right, have to go through an inverter to be able to come back to AC, match that frequency so that electricity can go onto the grid. Same thing in your microgrid. You have to balance that frequency. You have to be able to form your own grid. If you're not generating enough electricity, you may have to shed load. And so you have to prioritize which loads am I going to shed within, for example, my college campus. Do I shut down the dining hall or lose the dorms? In a industrial operation, do I lose my administrative offices? Do I shut down loads there? Or is there a particular process line that I know is not as critical as some of the other operations? Within just commercial buildings, again, you have to prioritize which things you want to load. HVAC, or do I dim the lights, or do I ask my neighbor to dim their lights or shut down their HVAC? All kinds of things with that. But also there's forecasting. So if you, again, in islanded mode, and let's say that you need to operate in islanded mode post-hurricane, for example. You get an estimate from your local utility that it's going to be 4 days before they can get the power back on to where you're located. Now, do you have 4 days worth of fuel? Hopefully you have planned for that. You do have, let's assume you have solar arrays on your property or somehow connected to your microgrid. So what's the solar irradiance forecast for the next couple of days? And how much energy storage capacity do I have in my battery? You want to forecast not only your loads but also your potential generation for that duration that you're anticipating. Transactive energy. This is another thing where if you have multiple, we'll call them accounts, right? And it could be houses. Probably easiest to think of it as a neighborhood. If you have a neighborhood that's all on a single feeder, somehow that's designed as a microgrid, but now some people have solar, some people have batteries, and they want to be able to trade electricity internally within their microgrid. How do you keep track of that? What's the value of that electricity when it's being traded? That concept is called transactive energy. Again, that's not widespread. There are a couple of small pilot projects around the country, but this is another feature that you can obtain within a microgrid that would be necessary as part of your operations and need to be designed into how you plan your microgrid. And then, of course, you're islanded right now, but you want to connect back to the grid, and that's called synchronization or resynchronization back to the grid. So when the grid comes up, they're going at 60 hertz. You may also be going at 60 hertz, but if they're not the same and you throw the switch, you get a boom. You don't want the boom. So you have to somehow be able to match that grid and then be able to reconnect. So operating a microgrid is also fairly complex. The good news is there's software out there that can help you design your microgrid. And this is a very short list, and there are dozens of consultants that will do this for you. Many of the microgrid providers, the ones that may provide some of the equipment to you as a microgrid operator, will also help with the design. I think the battery suppliers, or if you are considering like a generator set or even a large PV array, that they would also be able to help you do this. Homer is one of the oldest. It's been around since the 90s, I guess, maybe the late 80s. Spun out of the National Renewable Energy Lab, but is now a private company. Actually, Homer was recently acquired by Underwriter Laboratories, UL, which has their large certification facility out in RQP. Zindi, I think I'm saying that right, is the approved provider for many departments within the federal government. Then, there's also, you can also achieve microgrid design with your typical power systems analysis software packages like OpenDSS, like ETAP. Panda Power is an open source power analysis program, I think based out of Europe. But those are examples. The national labs, which are funded through the Department of Energy around the country. Oak Ridge is our closest one, but then there's also Sandia, Los Alamos, Pacific Northwest. There's maybe 17. There's a bunch of them. But they have all done some work in microgrids, almost each of them. National Renewable Energy Lab is another. And they've, several of them have put together these packages that are now freely available to you, the tax-paying public, if you wanted to design your own microgrid. I think the Sandia package is the microgrid design toolkit. I think maybe Lawrence Berkeley National Lab came up with what's called DuraCam. I know this is Distributed Energy Resources. I forget what the CAM stands for. But some of these are high-level tools where they will help you look at, okay, let's take a typical day and then forecast that out over a year, or pick up a typical day per month for your particular location. Look at your solar irradiance or potential wind, and then design things out that way. All the way down to super fine details that you would get from some of the larger vendors, ABB, Eaton, Schneider, Schweitzer, SEL, SNC Electric. There are lots of them that will design and build these microgrids for customers. But eventually, you will have to do what's called hardware in the loop. And this is a particular type of testing where you may not, most people wouldn't design their system within an HIL environment, but you would design it with one of these other software packages. And then you use some special equipment called HIL simulators. And I show two images of here of some of this special equipment. And what it allows you to do is it allows you to simulate in real time what it's like to be grid connected. It's essentially a power system in real time. And all these other packages, these are offline packages that do not show you how the grid interacts with power electronics or with solar variations in real time. It takes some special programming to be able to do this, but it's the only real way that you can have the confidence level you need in order to implement your design. You would use this for evaluation of all these different operating scenarios, as well as your protection schemes. So there are several companies that provide this. These are two pictures, like I said, from our lab. One of those is called Typhoon HIL, and this is their box, which works really well. This is a picture from one of our graduate student programs who integrated digital signal process controllers, DSP controllers, into the hardware that is now in the loop with the software environment that's running in real time on the Typhoon HIL. And then this is from, I cut off the name of the company, but this is Opal RT. And we use Opal RT environments, particularly for simulating high frequency power electronics, which are commonly in microgrid designs. So anyway, lots of software, but eventually you're going to need to do HIL, and there are companies out there that can work with you for that. But before you get there, you have to face some design decisions. Do I have an AC microgrid or a DC microgrid? Several of these generation sources that I mentioned earlier, including a battery and a PV array, right? The native output from those is direct current, not alternating current. But when you do that, you have to have an inverter that then matches the frequency of the AC grid. And if you chose to have a DC grid, DC microgrid design, it's simpler. It's certainly not as common, and there are other issues with that. But that's one of the decisions that you may have to make. And there can be some, I call them hybrid grids, that have certain portions that operate on a common DC bus, like this diagram, and then other portions that operate, at the regular AC. But you would have to have an inverter between the two. There are certain advantages for two-way power flow with these. That is easier to do or simpler to do, more efficient versus just a full AC design. You have to look at your type of battery when you're considering your design. If I am going to have a PV array, how big is my PV array, depending on the solar irradiance that I want to work on. If I'm going to have a diesel engine, a genset, how big of a storage tank do I have? And when you're considering resilience, one of the things you have to consider is do I have the contracts in place in order to get the diesel that may run out after 6 hours of operation, but I know I'm going to be without power for 4 days, but the roads are still flooded. That's a real life example from some of the resilience discussions that have been happening with that North Carolina resilience plan development. And then, wire sizing. I didn't even get into the protection stuff. There's all kinds of things, again, that a power systems engineer needs to consider as part of the design of a microgrid. So it's not simple. But now we're getting to the fun stuff. So I've told you how complicated it is, why you would need one, but still it's really hard to put together. It's, can be expensive because you have all of these different pieces that have to work together. And now, how do you control all of this? Let's even say you have the communications and you know what you want to happen when, but you have to have the control system, the brains of the operation, so to speak, to be able to manage all of these different devices. And when you get into control, again, there are different levels of control that need to occur within a microgrid. And this chart just basically goes through some of those. There's the power electronics tracking, which is obviously the fastest control, which may be your power electronics may be switching at kilohertz range, certainly, perhaps megahertz, depending on it. But those signals and those communications need to occur in the microsecond range, so 10 to the -6 seconds. And above that, you have what's called primary control, which is really, it's the power balance to make sure that all of your devices are either generating power or receiving power. Your loads are receiving the power that they need to balance both real and reactive power on the system. Above that is the voltage and frequency regulation. So am I still maintaining my set voltage? How do those signals happen? Well, they're happening in hundreds of milliseconds to seconds, again, depending upon the ability of your generation or load to respond to those particular signals. And then on top of that, you have to manage all of this for the total energy that's being consumed within the microgrid. Energy consumed by the loads, energy that remains in storage. You hate to be operating normally while your battery state of charge is slowly winding down. Some of us may have experienced this through, dealing with our phones. You're in the middle of typing a text, and then all of a sudden, things stop working because you weren't paying attention to how much battery you had left. So all of those pieces need to be included in a microgrid control system. So most microgrids today operate with a centralized controller. So there is a single computer, perhaps with a backup, that has communications running to it that then sends those signals out to your various devices. That's fine if your microgrid is localized. You do have to be aware that having a centralized controller is a small point of vulnerability. If something happens to that controller, or if a communication line is cut, then whatever has been cut from that microgrid may no longer be able to operate. And even though they may be able to receive power, if they're not receiving those commands from the controller, they wouldn't operate properly. So you would have to design in within the control system kind of the resiliency of, okay, we're operating islanded, or even we're operating grid connected. What happens if I lose communications? So these are the pieces that you need to manage. Most people have taken centralized control as their approach, but there's a different approach, and you can use a decentralized control approach. And now I'm going to tell you about the Resilient Information Architecture Platform for Smart Grids, RIAPS. And if you can't tell, this is so named by an academic, and we love our acronyms. Just to tell the origin story here, kind of like superheroes, but I know this is not quite Marvel quality, but maybe someday. We won an ARPA-E award, and we being Vanderbilt, NC State, and Washington State universities, to build a distributed, resilient, secure software platform that allows for computation at the edge and rapid deployment. Again, resilient information, we basically took those words and kind of combined them together. Resilient Information Architecture Platform for Smart Grids. And ARPA-E, by the way, is sort of the venture capital arm of the Department of Energy. They fund projects that don't fit into some of the other niches within the DOE programs that have great potential for success, but are also a little bit risky. So this is one of those risky ideas that has panned out well. But today, we've got these proprietary and custom solutions from many of the large vendors. There are many small vendors that are also creating their own microgrid platforms. But the issues that you run into is that there's limited interoperability among devices from these various vendors. There are common protocols that those devices may speak, but you lose functionality, you lose some of the ability for the control and capabilities of a lot of those devices if they're not all from the same vendor, which is why you'll see many utilities essentially get locked in to a particular vendor, for example, for their substation design, which is not bad inherently, but it can lead to problems if you want to switch to another vendor. Well, they may say, look, company B's product may be great, but it's not going to work with us, company A's control system. So an open system was preferred by the Department of Energy to help overcome some of these barriers. And so, like I said, if you can design something with open source, then it's going to provide this reusable chunk of code that allows you to move towards more of a plug and play architecture. And I probably need to clearly define open source. So open source means that the code is freely available. It does not mean that it is open for any hacker to be able to jump in. It does not, the open source is freely available. It does not mean that it's free to implement. As I've been describing, microgrids are very complicated. The software to design your own control system, yes, is now freely available, but you still have to, there's the cost of training on how to use it. You have to gain the experience on how to use it, that sort of stuff. So open does not equal free. Open does equal the potential for more applications, more functionality, and even more and sometimes faster support than you would receive even from a proprietary solution. Again, if the open source platform is very mature, there are thousands of people that may be contributing code and developing applications on that platform. But as things grow, you need to build up a community around that open source platform. So that's one of the things that we're trying to do as Vanderbilt and NC State is to build up a community around REOPS. But let me tell you a little bit more about the framework for how this stuff actually works. And a lot of this, I'm going to get a little computer science heavy as part of this, which I know is not the typical purview of some of the engineering disciplines, but bear with me for a little bit. So on the hardware platform, you will have an operating system kernel. In our case, we use Linux, which is an open source operating system platform. Some of you may have heard of a company called Red Hat. Red Hat made a gazillion dollars by figuring out how to sell an open source product to their customers, primarily through support, through server management, that kind of stuff. But Linux is what Red Hat is, Red Hat Linux. And so in our devices, in REOPS, we use a different flavor of Linux, but you have that kernel riding on the hardware platform. And then the actual REOPS body of the platform manages these two things called the component framework and the platform managers. I like to kind of, the analogy that they use within the open source world is that this is the plumbing, right? So this is the plumbing that helps to manage the flow through the pipes of the software. Another analogy is, I used Microsoft PowerPoint to build this presentation. PowerPoint could be viewed as the platform, but the content is all mine. And so it's something that allows you to create your own custom content. In this case, REOPS are the component framework and the platform managers here, but you build applications that run on this platform. And these applications can do all kinds of things. Remedial action scheme is usually something at the transmission level for utilities. You can do data analytics. You can do energy management across a distribution feeder or across a microgrid. You can use distributed SCADA, which is the control system that the control methodology that utilities have typically used. And then microgrid management is the focus of applications that NC State has built to work on this platform. So we built a REOPS microgrid controller that works on the platform. So just to be clear, the REOPS is not the microgrid controller, but you build applications that work on the platform that can, in essence, provide control for microgrids, among many of these other things. And each of these have been, these applications have been built by the university partners as part of the project. So, Ken, great, you're talking computer science. Tell me how this works. Well, again, if you're a computer scientist, this stuff is going to make you happy. There are software building blocks that are called components. It's actually just chunks of code that can be referenced multiple times within what are called actors, and you use these actors to build up to applications. The components, again, can be time triggered or event-based. There's a reason why it's single-threaded. No offense to power systems engineers, but they should not have to learn the functionality of multi-threading. I won't go into the explanation for that, but there's a reason for why we chose the single threading. But then these design decisions for the platform allow you to do the independent scheduling and prioritization for how these components operate. So everything is communicated through messages. You can have concurrent operations or concurrent execution on multiple nodes. So it is a truly distributed system. The platform managers handle things like time synchronization, right? If you think about all of those operations that we needed to achieve, turning on this device and turning on this device separated in space within your microgrid need to happen at the same time. How do you do that? Well, within the REOPS platform, you provide a synchronized clock, basically, so everybody knows what time it is. But then, there's a latency between when this node says, hey, I'm ready to turn on, let's do that in 2 seconds, and this node receives that 1 second later, but they know the time latency between nodes and agrees to turn on, 1 second later. So they both turn on 2 seconds after the decision is made. That's a super simple example, but time synchronization is really important. These other things, fault management, service discovery, how you deploy your applications onto the REOPS nodes, all of that again is handled by that plumbing on the REOPS platform. Same thing with service discovery. The ability for these nodes, which are really those hardware pieces, to be able to join or disconnect from the platform at any time makes it very resilient to changes in the microgrid. And when I mentioned open, I mentioned a little bit about cybersecurity. I don't think I used the word, but there are all kinds of cybersecure components to this, and that is an entirely other presentation that's probably twice as long as this one about all the cybersecurity features. Whether it's the elliptic curve algorithm used for encryption, whether it's unique hardware keys, whether it's the secure socket layer communications, all of those features are built in, by requirement. I mean, utilities are very sensitive to cybersecurity, and so this platform has all of that in it. But physically, we're talking about there's a device on a component of the grid, whether it's a load, a generation, or storage, that is associated with a single node. Each of those nodes communicates, whether it's a centralized REOPS node that's the controller or with their peers, and the nodes communicate between each other. This diagram is actually of, I mentioned that hardware in the loop. So when we deploy REOPS within the lab, we have used HIL simulators. This is a close-up of that. But this is the example of the hardware base that we use for REOPS. If you've heard of Raspberry Pi, which is a small Linux computer that's mostly used for educational projects, but has also branched out into much more complicated things, this is an upgrade from that. It's called the BeagleBone Black. And like I said, it's a small Linux computer. You see here, it's got your little micro USB. That's how you communicate to it. You put that in a little weatherproof box and attach it to the controller on your battery. And now that is a node within the REOPS control system. These little guys are like 60 bucks. So it's a very low cost way to provide a control system to multiple pieces of equipment within your microgrid. All right, so this is where I've talked about the framework. And I'm looking at my time here. I'm running out of time faster than I thought I would. So I'm probably going to breeze through these next few slides fairly quickly. This is just an example of what's called the Discovery Manager. So there's a communication network. These are essentially different communication buses that operate in the REOPS platform. There's component interactions, there's the discovery of applications, and then there's the execution control. Again, on each of those little beagle bones, it's running the REOPS application, which may have running the REOPS platform, which may have multiple applications running on it. But this is essentially a diagram to demonstrate that there's a discovery service when it detects nodes, when it detects new applications that need to be deployed to the nodes. That's just a very brief thing to show how it works. This again is some more details. Again, if you're a computer science guy, you would understand the pub-sub process. The application actually resides on all of these nodes. Only certain of the nodes are publishing information to a single subscriber that may then be using that global estimation to take action on its particular device or within the microgrid. I used to think that, coding was still like the days when I tried to learn Fortran, where you're sitting down writing individual lines of code. Not so much anymore. Now you are using development tools. So you actually have a REOPS plugin that works in your integrated development environment. In our case, we use a software package called Eclipse that helps you to build code and to deploy that code on your REOPS network. For the applications you build, there's also a validation and verification process that is sort of outside of this integrated development environment. But you build your applications, you test them outside of the environment, you then put them into the platform environment and can deploy that as a single package to your REOPS microgrid. Again, there are all kinds of tools to help you do this. This is very complicated, by the way. So not only are you a power systems engineer who understands how microgrids work, you also have to have some knowledge of computer science. A lot of power systems engineers already have that, but just to let you know, this is some of the complications in the knowledge base that's required to do some of these things, like resynchronization of a microgrid back to the main grid. So I described, several of those islanded operations. Resynchronization was one of those. This is a diagram of the decision tree, the logic tree for islanding, whether you've received a request from the grid or it's not received a request, and so it's an unplanned islanding status. In which case you need to operate as steady state mode as islanded and then be ready to reconnect when the main grid comes back. This again is fairly difficult. Most strategies do rely on a large distributed generation source, typically a diesel genset. And when I say large, it can be megawatts to be able to provide that frequency, and then all you have to do is you just have to match that one device, adjust the frequency of that one device to match what's coming on the grid. Once those are in sync, then you should be able to retransfer. There's a lot of other pieces that go before that. You want to do a lot of checks, but that's the process. In this case, maybe you have what's called a weak grid, where you don't have a dominant device, but you have multiple distributed energy resources in your grid. You've still got to manage voltage, magnitude, frequency, but match that real-time grid waveform. How do you do that? Well, you monitor the point of common coupling. Remember when we went through our microgrid definition, you monitor this, send a signal back to your one of the reops nodes that is kind of sending out a pulse signal to your other reops nodes, which will then match the frequency of your master node to be able to know when it's okay to close the transfer switch. Pinning consensus algorithm is essentially a mathematical way to get everybody to come to agreement. But you also have to, at the same time, still manage this active and reactive power, maintain stability of the grid while you're adjusting frequency of all these things. Again, fairly complicated, but this is an application that's been developed at NC State and deployed in that HIL environment where we've demonstrated the capabilities and demonstrated the stability. So when I say HIL environment, again, this is a few more details of exactly what the parts and pieces are. So in the interest of time, I am going to kind of breeze through this. Basically, you simulate the grid, you simulate your high frequency power electronics, you send signals to standard hardware that you'd find in a substation. Send that back to the communications network where you have all your little beagle bones that represent the reops nodes. Communicate however you need to, whatever protocol here, right? Modbus one way. There's another one where it's MQTT. This one is the C37 protocol for phasor measurement units to be able to match that voltage and frequency so you can resynchronize with the main grid. Let me talk briefly about open source. So I've talked about applications. I've explained how the reops platform works. As part of that, and being an open source platform, the reops software is a part of an effort by the Linux Foundation, which, if you don't know, the Linux Foundation is a global organization that has projects and in each of these areas and has really revolutionized a lot of these areas. Open source is really good when the problem is too big for any single company to solve. Think 5G, think autonomous vehicles, think blockchain. Linux Foundation has projects in all of these where companies that may be competitors all contribute code to this base layer that then provides the core functionality that they were all going to duplicate anyway, but it frees them up from focusing on that part and then be able to focus on their particular value add to the platform. Well, Linux has now gotten into energy. This is a quote about Phil Jackson, if anybody gets basketball references. Linux Foundation is now focused on energy, and they have multiple software packages that cover everything from how operators react to alerts, substation automation, how you do asset tracking and management as a utility, how you do distribution system design, or even parts of your planning for utility operations. Energy meter data, how is that managed? I mean, these are all grid functions that are now have open source software applications that are building up the functionality to allow utilities to participate. And here's REOPS. Yes, we're the edge node control platform. So I mentioned building up the community. Hopefully that's what we're going to achieve through participating in the Linux Foundation Energy project. So very quickly, I realize, Katie, I've got 5 minutes left, and hopefully you're keeping track of all of the questions, if there are any, if I haven't bored everyone to death. I didn't mention my office mate earlier. It's my dog, and he's usually asleep. Once I start talking, he goes to sleep. I'm not offended. But in summary, microgrids, very resilient, but complicated. Current control systems, proprietary and expensive. But the DOE said, hey, we need something that's resilient, secure, and distributed with multiple hardware options, and it's adaptable to multiple programming languages as well. So that's why we built REOPS. As my last slide right here, these are some references. If you want to learn more, you can go to this website for REOPS. This stands for Institute for System Information and Structures, or something like that. It was named a long time ago. It's just unfortunate. GitHub is the primary repository for open source code. You can go there if you really want to see how all that stuff works. There are dozens of IEEE papers, but if you're like me and like to watch videos, NC State ECE YouTube channel has several, and REOPS has its own YouTube channel as well, where you can learn more. And there's some really great examples of demonstrations of the software applications on the REOPS YouTube channel.
All right, we've got some questions coming through now, Ken. How do you protect a microgrid against expected intermittent recloser operation on the grid to which it is connected, especially the islanding reconnection required to ride through momentary outages?
So that would be part of your controls, where again, if it is a momentary, you would have to make a decision, do I island even for a momentary? If your operations cannot even stand a power blink, then you would have some sort of buffer essentially between yourself and the grid for that. If it's a residence, you're not going to kick in your microgrid just because the lights blink. You would have some other sort of delay, kind of like I described where NC State, I mean, their delay is 4 hours, basically because for them to power up the microgrid, it would cost too much for them to do that, or it's a timing thing where they do have a longer delay. So that's a good question, but again, it all depends upon your particular situation and the design of your grid.
Okay, is your code available for download on GitHub?
Yes, it is. Right there, github.com/RIAPS. I like that question.
As an outcome of the Paris Agreement, many organizations have committed to net zero carbon by 2050. From a technical standpoint, how do microgrids contribute to the net zero goal or the general effort to limit the temperature rise well below 2 degrees?
It's a way that you can integrate more distributed energy resources like renewables. It's not specific to that, meaning you can also, power your microgrid with a diesel generator. But again, with the free cost of renewable energy, if you can form a microgrid and essentially stack those services, provide services back to the grid, participate in demand response programs, then it makes it more, it gives you more financial incentive to include some of those distributed energy resources like renewables into your microgrid. So microgrids are not the single answer for how companies or countries meet their Paris goals, but it is a piece that we think with the right control system that may lower the cost for microgrids can really enable a lot more renewable resources to connect through microgrids where they can provide those benefits. So it's not the silver bullet, but it's a piece of that silver buckshot that's hopefully going to help us reach our Paris Agreement.
Great. All right. Well, that's all of the questions. Ken, thank you so much for your time today. We really appreciate it.
Okay.
Everyone on the call, your PDH forms will be emailed out to you shortly. Our last session today will start at 4 p.m. It is the water quality case for paved streamside greenway trails. Ken, thanks again. Have a great day.
Thank you. See you.